Hello, everybody, and welcome back to another video in Geography 340 Climatology. I'm Dr. Zach Hilgendorf, and in this video, we're going to be talking about mid-latitude cyclones. We've been setting up for this over the last couple of videos, talking about how air masses rise and are moved throughout the atmosphere, different types of clouds, different types of precipitation. We talked in the last video a little bit more in depth about frontal systems. And now we're kind of getting into mid-latitude cyclones, which are really a product of these different interactions within the atmosphere. Again, as I mentioned in the last video, a lot of really great resources went into making this video and these last couple in particular. Professor Ian M. Brooks, University of Leeds, provided some materials for me, which I'm very grateful for. Eric Snodgrass, formerly of UIUC, had some posted materials as well. I grabbed a lot from the National Weather Service and the National Oceanic and Atmospheric Administration. So a quick recap of where we were in our last video. We started and talked about the different types of frontal systems. So warm fronts tend to move slower than cold fronts and are the leading edge of warm air moving northward. Before the front passes, winds are easterly. Cloud cover may be heavy ahead of the front, with rainfall chances increasing as it approaches. Temperatures will warm rapidly with the clouds clearing after the front passes through. With the warm air comes higher humidity as well. Cold front is the leading edge of a colder air mass. Temperatures will usually change rapidly over a short distance with a cold front moving through. Also, there's a sharp change in moisture content. Higher moisture content ahead of the front and lower moisture content behind it. Shifts in wind direction are significant in identifying a cold front. Thunderstorms sometimes develop ahead of these fronts as the warm air ahead of the front rises over the colder air. Another type of front can be found as known as a stationary front. In this front, neither the cold air mass nor the warm air mass is moving. Winds tend to blow along it in opposing directions on either side. Conditions along the front are clear and dry. However, if moisture is available near the front, clouds and light precipitation may develop. And then an occluded front occurs when a cold front overtakes a warm front. There are both cold and warm occlusions. In a cold occlusion, the colder air is found behind the front. Conversely, a warm occlusion is characterized by warmer air located behind the front. So in the last video, we ended here, kind of calling out this circle from the map, from the chart and map on the 7 a.m. to 7 a.m. on the 27th of November to the 28th of November. We see here a cold front that has intersected this warm front and led to this occlusion. And what this looks to be, especially because we see rain and thunderstorms abound in that entire region along from Florida up through Pennsylvania all the way over to Missouri, we see rain and thunderstorms, which would be a good indication that we are looking at a mid-latitude cyclone. And that's what our video is going to focus on today, mid-latitude cyclones. We actually see a couple in our little map here. If I can circle it here. There's one. Kind of tough to see, but it appears like there's another over there. And there might be one off on this edge over here. So mid-latitude cyclones are basically low pressure systems that are characterized, a characteristic feature of mid-latitude temperate zones, right? Their name kind of says it all. They happen in the mid-latitudes, roughly 30 to 60 degrees north and south latitude. They form in well-defined zones associated with the polar front, which provides a strong temperature gradient and convergent flow resulting from these global circulation patterns that we've been talking about for a number of weeks now. We can see an example of one here, kind of looking over the UK. And we can see these different associated fronts. There's a cold front and a stationary front, in this case, related to the development and evolution of this mid-latitude cyclone. So we look at them from a two-dimensional sense. And we can see here, kind of starting out, this is the starting point of the development and evolution of a mid-latitude cyclone. So that top graphic there, we see low pressure forms at the surface over a polar front due to divergence of air aloft. As rotation around initial low points start, a wave will develop on the polar front. We can see kind of that little nick there, or that little bump in the frontal system there. So we go from a stationary front, we see there in the top, to kind of this maybe occluded front, or this intersecting warm low front here, with that developing low centered in the middle of the front. We see cloud formation beginning here. So friction effects cause surface flow around the low point to converge, the low pressure to converge. And then, given mass balance, inward flow is compensated by large-scale lifting and cooling and cloud formation. So that's what we see in that bottom graphic there. Moving on, we go to kind of maybe step 3 here. That surface low is maintained or deepens due to divergence of airs aloft and exceeding convergence at the surface. Flow is super geostrophic, meaning there's a cold sector air that is pushing the cold front forward, and warm sector air flows up the warm front, and then the warm front moves slower than the cold front. In number 4, we see broader development of our cloud cover, and the cold front overtakes the warm front to form an occlusion. That's what we're seeing kind of from the L to the point where the two meet, right here. So this feature here is our occlusion that we're talking about here. So this works out from the center of the front here and the developing mid-latitude cyclone. And the depression usually achieves maximum intensity about 12 to 24 hours after the start of that occluded front. Moving forward, the low starts to weaken as inflowing air fills up the low pressure. Remember, we're trying to basically just equilibrate, right? If we have these low pressure zones, we have proximal areas of high pressure where air is rushing in to try and fill these zones up. So once it happens, we basically weaken and destroy that system because our air pressure has equilibrated. And then in the last one, the low continues to weaken, the clouds begin to break up. And that's kind of the life cycle, or the two-dimensional life cycle of one of these mid-latitude cyclones. Now we can look at it from a more three-dimensional perspective. So we're going to look at 2 separate diagrams here, and here is the first one. So in this case, we see kind of our cold and warm front, maybe our stationary front here, as these two are meeting. We see as things start to develop and that circulation begins to occur, see a kind of a sharpening of those two different frontal systems. If we look from A to B, we can see that cold air mass wedging underneath that warm air mass, with warmer air rising as it does. And then as the system begins, we have kind of what we would call cyclogenesis, or that circling formation. As you know, mid-latitude cyclone, it needs to cycle. So as that cyclogenesis develops, we can kind of see that cold front pushes in more. We see cooler air near the surface kind of wedging in, that warm air aloft, condensing. That's where we're seeing a lot of our cloud development and precipitation occurring. So that's, again, from A to B. And then we kind of complete it there. We see the more cyclogenesis occurring as that system is kind of taken hold. And we see the warm front on kind of that outward edge, the cold front moving through. Moving into our second diagram here. So here we can see, we know that in the mid-latitudes, there's a boundary between our cold, dry, or continental polar, if we recall from the last video, air to the north, and the warm, moist, or maritime tropical air to the south. We see the stationary front here, where cold air is moving from right to left, warm air is moving from left to right. Along this boundary, a counterclockwise circulation can set up at the surface, which acts to take warm air up from the south and cold air down from the north. This is how we get that cyclogenesis that I just mentioned. In the center of the circulation, there is mass convergence. All of the air is moving in towards the center of circulation, much like when you make a whirlpool in a pool. All the leaves and stuff that's kind of floating around you will move towards the center. Think of that as kind of our cyclogenesis. When all that air hits the center, we have rising motion because that air has nowhere else to go. If the upper levels are favorable for cyclone development, then there is a region of divergence aloft above the developing low pressure center. This will help pull the air that's converging at the surface upwards and continue to develop the surface cyclone. The upper levels also steer the system and make it progress east, like we talked about earlier. If the upper levels aren't favorable for cyclone development, the cyclone won't grow and the mass convergence into the low at the surface will just pile up and fill the low pressure. So basically we'll have a decaying of the system. Here. If the upper levels are favorable, then the mid-latitude cyclone will continue to develop and bring up the moist tropical air in the warm sector and bring down the cold continental polar air in the cold sector. The maritime tropical air rises as it moves out ahead of the low, helping to deepen the low pressure center to the east and help it move along. The continental polar air sinks behind the system and fills in the low pressure on the backside, if we remember cold air descending, also helping to move the system forward. Once the mid-latitude cyclones fully developed, well-defined fronts appear, and we can see these fronts here pretty well, the stationary front, cold front, warm front. As the mid-latitude cyclone reaches maturity, the central pressure will be at its lowest, and the occluded front will begin to form as the cold air catches up to the warm front. And then once the system is occluded, all the warm air is above the cold air, mass convergence acts to fill in that low pressure zone, and the system decays. In typical winter patterns, this is what we would see with a mid-latitude cyclone. We look at upper air, so that's just kind of upper atmosphere winds, so maybe like 500 millibar winds, kind of half of our atmospheric density. So we see these high and low pressure systems, so upper ridge, upper trough, kind of this meandering pattern in the upper atmosphere where air is converging and diverging. Relative to what's going on the surface, we can see a couple of different things. From a cloud perspective, if you're towards the east the west edge of this map, if we're assuming north is up, or the left edge of this map, you can see milky skies from the cloud perspective off to the left or west. We see clearing skies kind of towards the left edge of that cold front, that thin band that we've talked about. Clouds increasing as you move kind of towards the bottom right of our little image. Clouds thickening in the form of often nimbostratus or cumulonimbus clouds to the top right. And then that entire area where you see showers or precipitation, that would be fully cloud covered. We have rising pressure behind the front or behind the cold front. We see that high pressure system there. Where the low pressure system predominates, we have falling pressure. We see warm air down over here. Makes sense, kind of behind the warm front, where you have a wedge of cold air coming in over here. If this, again, is in winter, in this portion, we might have winter snow, where over here, we might have just rain, precipitation. We see that here too, showers instead of snowfall. And then with that high pressure system, clear skies kind of predominate at the very end. So now looking at typical mid-latitude cyclone paths for our North American winter. So we notice a couple different names here. We see Gulf of Alaska low, Alberta Clipper, Colorado low, Gulf low, and Hatteras low. So these are some typical names that we've given because of the typical paths that these follow in our winter months. So if you're on the lee side of the Rockies, so downwind of the Rockies, in our case, east of the Rockies, you might see lee cyclones. So Alberta Clippers, these are fast moving. They have little precipitation given distance from any source of moisture. Our Colorado low is an intense low system with strong warm area advection in the warm sector, very cold temps in the cold sector. If there's a lot of Gulf moisture, you usually have sleet, freezing rain, and rain along the warm front, and very strong thunderstorms along the cold front, and snow along the backside of our Colorado low. Our Gulf low, these are along the east coast, form along the southern coast where there's a thermal boundary between the warm ocean and cool land. Usually there's a lot of precipitation because of this system's proximity to a moisture source, i.e. the ocean. Hatteras low and nor'easters. These are the most intense systems that form along thermal boundaries between the warm Gulf air and the cold Atlantic coast. These can bring flooding along the coast and feet of snow inland using the ocean as a vast source of moisture. This is where you've likely or may have heard of the term bomb cyclone. What is a bomb cyclone? Because that's a pretty colorful and sensational word. Well, what it basically means is the rapid or explosive intensification of a mid-latitude system. Bombogenesis, which is an actual term, occurs when a mid-latitude cyclone rapidly or explosively intensifies over a 24-hour period. This is typically, but not always, accelerating and strengthening over the ocean, and central pressure within that system drops at least 24 millibars in 24 hours. We see an example of one that was moving across the southern portion of the country in mid-March of 2019, kind of taking this path here, if you can kind of see my map there. So you'll see it come into view right there. So that system kind of pushes up. Apologies. Looks like the trajectory was maybe a little bit closer to that. Oh, trying to delete. There we go. Our trajectory is a little bit closer to that, it looks like. So we can see the system pushing up through New Mexico, Texas, Oklahoma, kind of into Kansas, Nebraska area. This was a pretty big one, actually. So this bomb cyclone on the 13th of March, 2019, developed over southern Colorado. The recorded low was actually a record low for the state of Colorado, 970.4 millibars. Think of typical sea level 100 or 1021 or sorry, 1012-ish millibars, so pretty low. Gusts ranged from 60 to 100 miles per hour with 1 to 3 feet of snow being dumped in some of the mountain regions. Over 1,400 flights were canceled out of Denver International, waylaying about 5,000 passengers. All of the major highways and interstates from Denver were closed, some from Denver all the way to Nebraska and Kansas down through Colorado Springs. So some tons and tons of closures. Multi-car accidents were numerous. Over 1,500 people were stranded in their cars. Trees and power lines were blown down. At one time, it peaked with about 445,000 people out of power. And then there was one known fatality, and that was a Colorado State Trooper, who I believe was hit in the line of duty. So if we kind of boil it down here, mid-latitude versus tropical cyclones. We don't have anything for tropical cyclones yet because you'll see this graph being filled in the next video. So for mid-latitude cyclones, other names we can think of for these would be frontal depressions, temperate cyclones, or extratropical cyclones. They form between 40 degrees north, or 40 to 60 degrees north and south latitude. They typically occur because they can kind of move outside of that depending on their trajectory between 30 and 60 degrees north and south latitude. Their movement is west to east, driven and pushed by westerly winds. They occur all year round in both hemispheres. Their identifying features are a warm front and a warm sector with a cold front and a cold sector. And then for weather, weather associated with a cold front is overcast, low temperatures, strong winds, and heavy rain. So in the next video, obviously, we're going to be talking about tropical cyclones, focusing primarily on hurricanes. So I hope you enjoyed this video, and we will see you in the next one. All right, bye.